We saw in our previous video that the problem of telling whether there's an Eulerian path through a graph that crosses every link exactly once is something we can solve quite quickly just by checking to see the number of edges that touch each vertex. But we claimed that the Hamiltonian path problem, where we need to visit each vertex exactly once, takes an enormous amount of search, potentially an exponentially large amount of search if the graph is large. In this video, we're going to talk about these polynomials versus exponentials and why they matter so much. So a polynomial function of n, if n is the size of the example of the problem you're trying to solve, for instance, the number of links or the number of nodes in a graph that you're trying to tour, a polynomial function doesn't grow too badly as n grows. So the simplest polynomial of n is n to the first power. It just grows linearly as n increases. N squared grows like the area of a square, and so yes, it grows, and n cubed grows like the volume of a cube, but this is much smaller still than exponential growth. Now here is a classic illustration of exponential growth. Legend has it that the Emperor of India was so grateful to the inventor of chess for inventing a great game that he offered to reward the inventor with anything they liked. The inventor said, well, people in my village are kind of hungry. I would like to have a chessboard with 1 grain of rice on the first square, 2 on the second square, 4 on the next, 8 on the next, and so on, doubling each time. The Emperor said, no problem, make it so. The problem is that after only 20 squares, we already have more than 1 million grains of rice. After 30, we have more than 1 billion. And in order to cover the entire chessboard, we have about 18 quintillion grains of rice, which is more than all the rice in the universe, even if there are other planets with rice. So this is the kind of growth which we don't want to have in the amount of computation that we need to do to solve a problem.